Okay, can we continue?
Yes, sir.
So we introduced the parametric model that we want to exploit. The parametric model was a parametric model of the spatial correlation matrix, and in particular, we parameterize the spatial correlation matrix of the signal of interest as function of the unknown direction arrival. And we applied the nonlinear least square method to estimate the direction arrival by using this parametric model. The other thing that we prove is that if the sources are well separated, so it was the last few graph. So this is the maximization, k-dimensional maximization problem that we have to solve to find an estimate of the direction arrival. So we first estimate the sample covariance matrix, and then we use the estimated matrix to calculate this functional, and we solve this nonlinear maximization problem, and we find the angle of arrival. What we prove is that if the sources are well separated, so the respective spatial frequencies are spaced by more than 1 over m, then the nonlinear least square estimates can be derived with good approximation by applying the classical beamformer. So by estimating the spatial power spectral density with respect to theta, and then the functional becomes one-dimensional because it does not depend on, it's not k-dimensional where k is the number of targets, but basically the single search, the single k-dimensional search is replaced by k one-dimensional search, because we have just to search for the location of the k largest peak in the estimated power spectral density. So find the k largest peak, it means that we have to solve k one-dimensional maximization problems. So we find the highest peak, then the second, then the third, and so on. And the reduction in computational complexity is huge, And moreover, if the array is Euler, things are even better from the computational complexity point of view, because if you remember, the estimated spatial power spectral density that is given by this expression can be expressed as the average of the periodograms, and so each periodogram can be calculated by the fast Fourier transform. So we take the snapshot, we calculate the fast Fourier transform, then modulo square divided by the number of sensors. We do this for all the snapshots, and then we average. The fact that we can use the fast Fourier transform allows a significant reduction of the computational complexity. So, I mean, this is very important. The only problem of the classical beamforming, remember, is the resolution. which is limited by the number of sensors, because the resolution, which is called Rayleigh limit, is 1/m. Okay, so we derived the non-linearly square solution, but you may remember is that if what we observe is signal plus additive white Gaussian noise, and we want to estimate parameter of the signal, in that particular case where the noise is additive white and Gaussian, the non-linearly square solution coincides with the maximum likelihood estimate. And these are, I mean, this would be quite positive, because we know that all maximum likelihood estimates have some very nice properties. Because all, I mean, under very weak condition, all maximum likelihood estimates are asymptotically unbiased, are asymptotically Gaussian, so we know the asymptotic distribution, asymptotically efficient, so it means that the mean square error of the estimator tends to the well-known Kramer-Rao lower bound, which represents the lowest possible mean square error that can be achieved by any unbiased estimator. And finally, all maximum likelihood estimates are consistent. So the mean square error tends to 0 when the data size tends to infinity, so the estimate tends to the true value. The estimator that I show you, that I derived by using the nonlinearly square principle, sometimes is also known as the deterministic maximum likelihood estimator or conditional maximum likelihood estimator. Why? Because it has been derived under the assumption that the signal vectors are deterministic. The other possibility is that, as I told you before, is that we assume that the signal are modeled as a random quantity, unknown random. So far, we assume that they are unknown deterministic. Clearly, once the direction arrival have been estimated, we can estimate, we can use basically the maximum likelihood estimator for the noise power. And this is, I mean, I skipped the proof, but this is the maximum likelihood estimator of the noise power, if the noise is additive white and Gaussian. Otherwise, it's a non-linearly square estimator. So once we have estimated theta, we can estimate the noise power. Okay. The other option is that we model the signal as a Gaussian process. And in particular, the assumption that has been done is that it's a white Gaussian process. So it's a sequence of independent and identically distributed Gaussian samples. So in other words, both the signal generated by the sources and the noise are white Gaussian processes. Okay. The maximum likelihood estimator that is derived under this assumption is called stochastic maximum likelihood, because it relies on a random model of the source signals. So if we assume that the signal is modeled as a Gaussian random vector with 0 mean, and the spatial covariance matrix is Rs, So RS is the spatial covariance matrix of the sources. If the processes are white processes, the sources are temporally white processes. So they are white in time, but obviously not in space. So if the noise is also modeled as a white Gaussian noise, it's very easy to write down the joint probability density function. Remember, if you want to derive the maximum likelihood estimator, first we have to derive the joint probability density function of all the data, and then we have to maximize the PDF with respect to the unknown parameters. So under these assumptions, so if both the noise and the signal are temporally wide, the joint PDF is the product of the PDF of the n different snapshot. And each of them is Gaussian with zero mean and covariance matrix Ry. And Ry is the well-known covariance matrix that, we have derived in the past. So to find the maximum likelihood estimator, we can calculate the log likelihood, so the logarithm of the PDF, and then we can maximize the logarithm of the PDF. Maximize the logarithm of the PDF means minimizing this quantity here with respect to the unknown parameters. The unknown parameters are the direction arrival, the spatial covariance matrix of the signal, and the noise power. Now, I skipped all the details of the derivation because they are quite lengthy and can be found in books, in papers. I just want to report the solution, and the solution is the following. We can express the maximum likelihood estimator of the noise power and of the matrix RS as a function of theta in this way. So these are the expression of the two maximum likelihood estimator as a function of theta. So then we replace these in the functional. So we eliminate the dependency on RS and sigma W. So, and we come up with a compressed functional that depends only on the direction arrival. And this is the, skipping all the details, this is the function. So we have to plug here and here these two expressions. So at the end, we have something that depends only on theta. We solve this optimization problem with respect to theta. Again, it's a k-dimensional optimization problem. So the problem are the same as the deterministic maximum likelihood, more or less. And then we find the solution. Once we find an estimate of theta, we plug the estimate of theta here, and we find an estimate of these other parameters. I reported the final expression. Why? Because people have proved that the performance that we achieve by using the stochastic approach, so by estimating the direction arrival by using this, are always better than the performance of the deterministic maximum likelihood. And this is true even when the signal are not Gaussian or are not wide. So this result is pretty robust and provides very accurate estimate of the direction arrival at the cost of clearly very high computational complexity. So this is the problem. The performance can be compared with the Kramer-Rao bound and again, I skipped all the results of the, I skipped all the details, sorry, of the derivation, and I just reported the final expression of the Kramer-Rao bound, because then I plot some numerical results and I also plot the Kramer-Rao bound. So this is the Kramer-Rao bound that I plot, and this is the Kramer-Rao bound on the estimate of theta under the assumption that the signal are Gaussian processes. So under the assumption made to derive the stochastic maximum likelihood estimator. So we understood that both the deterministic maximum likelihood or non-linearly squared, they are the same. And the stochastic maximum likelihood have very good performance. So they have a mean square error that is close to the Kramer-Rao bound. So they are asymptotically efficient. So the problem is not the estimation accuracy, but the problem is the computational complexity. In order to find the solution, we have to apply a numerical method, numerical optimization method. There are many methods that have been proposed in the literature to solve these kind of problems. I will not enter in the details. I just want to mention the name of the most widely adopted method. And they are the expectation maximization, the alternating projection, the space alternating generalized expectation, SAGE, relax, and also the iterative quadratic maximum likelihood, IQML. And these are all iterative methods of the kind of the Newton method. So they use the gradient and something like this. And I repeat, they are iterative. And most of these methods basically have exploit the idea that instead of estimating altogether all the unknown parameters, so instead of solving a maximization problem with respect to all parameters, in sequence, we estimate only a subset of parameters. So for example, if there are k sources, we first estimate the parameters of the first source, and then we eliminate from the data the first source. Then we estimate the parameters of the second source, and so on. And we repeat this iteratively. Globally, the computational complexity is reduced, and most of this method converges, if properly initialized, to the right solution. If you are curious, you can find more details about this method in the literature. There are other methods that have been proposed, which are quite interesting. The subspace fitting method, the weighted subspace method, the method of direction estimation mode. And they try to solve this very high complexity problem in an efficient manner. I want to focus on a class of methods that achieve almost optimal estimation accuracy, but with a computational complexity that is much, much lower than maximum likelihood. And these are the so-called subspace methods. Now, the idea of, in general, of these subspace-based methods is to exploit the geometrical properties of the model of the correlation matrix. And to exploit the properties of the correlation matrix in an explicit way, differently from what you have seen with adaptive beamforming techniques. And it has been proved that by properly exploiting the properties of the correlation matrix of the data, subspace method can achieve a resolution that is better than the classical Rayleigh resolution. That's why, for this reason, they are called super resolution methods. So subspace-based methods are model-based method that exploits the properties of the covariance matrix of the data and achieve a resolution that is better than the resolution of the classical method, so better than the Rayleigh limit. For this reason, they are called super resolution method. Now, even within the class of subspace-based method, there are different kinds of method, depending on how they find the solution. So there are the so-called extrema searching techniques, and spectral music belongs to this class. There are polynomial routing techniques, and root music belong to this class. I'm mentioning those that I will describe in detail. And then there are matrix shifting techniques, and esprit belong to this class. In the view graph, you can also find the derivation of spatial Uli Walker, but I will skip it. So now I want to describe in detail one method for each one of these three classes. So I will describe in detail spectral music, then root music, and then esprit, and then compare them. There are others you can see in this view graph, but I mean, if you are curious, you can find in the literature more details on these other methods. So I will focus only on these three, obviously for lack of time. Okay, let's talk about music. Music was originally proposed in the spatial domain, actually, to estimate the directional arrival of signals. And then it has been applied also in the temporal domain to estimate the frequency of a multi-component sinusoidal signal. Music is the contraction of multiple signal classification. There are two kinds of music, as I said, spectral music and root music. The difference, and you will understand why. I mean, there are some differences, but the most important difference is that spectral music can be used for any array geometry. Root music can be used only with uniform linear arrays. Both of them has a weakness, and the weakness is that, like Capon, we have seen this yesterday, this algorithm does not perform well if there are sources that are highly correlated. And the reason is that if there are very highly correlated sources, it is no more true that the rank of the spatial correlation matrix RS is equal to the number of sources. The rank becomes smaller, and this creates problem to Capon, but also to music, as you will see. Luckily, I mean, there are methods to overcome this problem. So there are versions of music that in some way overcome this problem. They are called spatial smoothing music and forward-backward spatial smoothing music. So they are modification of music where, at the cost of higher computational complexity and a worsening of the resolution, but they work well even if there are coherent sources. Okay, let's describe music. First, assuming that the K sources are uncorrelated. So if the K sources are uncorrelated, the covariance matrix of the signal is diagonal. And on the main diagonal, you have the power of the K sources. So in this case, the rank of the signal correlation matrix is equal to K. Obviously, if M is greater than K, because otherwise, in general, the rank is the minimum between M and K, but the number of sensors should be always greater than the number of sources. So in this case, the rank of this matrix is equal to the rank of Rs, which is K. Now, if this matrix has K eigenvalues, because it's an Hermitian matrix, this matrix is M by M. So if the rank is K, it means that this matrix should have K eigenvalues different from 0. And because the matrix is Hermitian, these K eigenvalues should be positive. So this matrix should have K positive eigenvalues and the other M minus K 0. Why? Because it's a property of the matrices. The rank is equal to the number of non-zero eigenvalues. So let's assume that we order them in decreasing order. So lambda tilde 1, lambda tilde 2, and so on, up to lambda tilde k. Then covariance matrix of the data is obtained by adding this matrix, which is diagonal. So when you add this matrix, basically you obtain a matrix with eigenvalues equal to the previous eigenvalues plus the noise power. This is the effect of summing the identity matrix. So what happened? It happened that the spectrum of the eigenvalues of the data covariance matrix decreases from k equal 1 to k equal capital K, and then have a floor. So all the eigenvalues from k plus 1 to m are constant, and the value of this constant is the noise power. Now, if we call S1, S2 up to Sk, the eigenvectors of the matrix associated to the first k eigenvalues, and we put them in a matrix, what we obtain is an m by k orthonormal matrix. because we know all the eigenvector have unit norm and they are mutually orthogonal. This is true if these eigenvalues are all different. Now, the matrix S generates a subspace of dimension k, because they are k columns, and this is called signal subspace because it is the subspace generated by the eigenvectors associated to the eigenvalues of the signal different from 0. So if you multiply the covariance matrix by one of the signal eigenvectors, what you get is the associated eigenvalue times sk. This is the definition of eigenvector eigenvalue. Now, if we call sk plus 1, sk plus 2 up to Sm, the other m minus k eigenvector associated to the noise eigenvalues, so associated to these eigenvalues that are all equal, and we define G, the m times m minus k dimensional matrix. This is a matrix where each column has norm 1 and they are mutually orthogonal. So this matrix represents an orthonormal base for the subspace orthogonal to the signal subspace, and we call this noise subspace. Clearly, if you multiply the covariance matrix by one of the noise eigenvectors, because they are orthogonal to the others, when you multiply A Hermitian by Sk, it is 0. And what you get is only sigma W squared times Sk. And this is true, I repeat, for any k that goes from capital K plus 1 to M. You can repeat this for any k, so you can write this relationship. R epsilon G equal sigma W squared G. R epsilon G can also be expressed in this way. And so it is A RS A Hermitian G plus sigma W squared G. And this should be equal to sigma W squared G. It should be equal to this. And so it means that basically the subspace generated by the column of A should be orthogonal to the noise subspace. So if it should be orthogonal to the noise subspace, it means that if you calculate, so remember the structure of this. So this is A of theta, somewhere is reported. Okay. So A of theta is the steering matrix. So if this is 0, it should be 0 for any column of A. So for the array response calculated for all the directional arrival of the K sources. So, in other words, all the K columns of the matrix A, of the steering matrix, they generate the signal subspace, which is k-dimensional. This is obviously true if Rs is full rank, for the reason I said before. The eigenvectors of the covariance matrix that corresponds to the other n minus k smallest eigenvalues are orthogonal to the signal subspace, and they generate the noise subspace. The eigenvectors of the matrix that correspond to the k largest eigenvalues span the signal subspace. So span the same subspace generated by the column of A. So in other words, the signal subspace is generated by the column of A, and the eigenvectors that are in S represents an orthonormal base for this subspace, and the range is the same. Now, if these two matrices have the same range, so if they generate the same subspace, it means, this is a well-known property of matrices, it means that it should exist a non-singular matrix C, a square full-rank matrix C, such that A is obtained from S by post-multiplying S by C. So if the range is the same, it must exist C such that this is true. Now, because G is the matrix whose column represents an orthonormal base for the noise subspace, which is orthogonal, this quantity here should be 0 all the times theta is equal to 1 of the direction arrival of the k sources. So if this is 0, this is a vector, the Euclidean norm of this vector should be 0, or the Euclidean norm square should be 0. Now, this is exactly true if G is perfectly known. The problem is that G should be obtained from the data. And if you obtain G from the data, this equality, I mean, this quantity will not be exactly 0. We expect to be small. So once we replace here the estimated G, the idea could be find the K smallest, the value of theta for which this quantity is the smallest. Instead of searching the minimum of this quantity, the idea of music is search for the location of the K highest peak in the reciprocal. So at the end, to summarize, so the spatial music method is organized in these steps. The first step is to estimate the spatial covariance matrix of the data. So it is the sample covariance matrix. It can be expressed in matrix notation if you define Y, the matrix Y, as the data matrix. So it's a M by N data matrix. So you put all the snapshots one after the other. So if you build Y in this way, you can express the sample covariance matrix as 1 over N Y hermita. So you calculate this matrix, then you calculate the eigenvector decomposition, you take the eigenvectors associated to the k largest eigenvalues, so you have S, and the other n minus k eigenvectors are the noise eigenvector. Music uses the noise eigenvector, so G hat. So you extract G hat from the decomposition, and then you calculate this functional, the Euclidean norm square of A emitting of theta with multiply G hat. So it's a function of theta. You put this at the denominator, and so the estimate of the k directional arrival is given by the position of the k largest peak. This method is called spectral music because in some way it mimics what we have seen with Capon and classical beamforming. So we derive a spectrum, and then we find the position of the peak. This quantity here is called pseudo spectrum because actually it's not a spectrum. So it's not important the shape of this functional. The only thing that matters is the position of the k largest peak. So there is no information in the shape of the spectrum. So it's a sort of spectrum, but I mean, except for the position of the peak, it does not bring any useful information. That's why it is called pseudo spectrum, and the method, it is called spectral music. So when is okay? It can be proved that this method is consistent because when the number of snapshots tends to infinity, the matrix is perfectly estimated. So G hat tends to the true G, and so the position of the peak and the pseudo spectrum are exactly equal to the true directional arrival. So music, it has been proved, it's a consistent estimator. In general, it has better resolution than Capon and beamforming, but obviously, I mean, the resolution is limited, and it depends on the number of snapshots, it depends on the signal-to-noise ratio, and so on. This version of music works well only if the rank of RS is equal to the number of sources. So if RS is a full rank matrix. If it is not, so in the presence of, for example, multipath, this method does not work. So we have to use, in that case, modified version of music. So this is spectral music. How do we derive root music, and which are pros and cons of root music with respect to spectral music? If the array is Euler, so remember, root music can be used only if the array is Euler. If the array is Euler, the array response is made like this. This is the structure of the array response if the array is Euler. Now, you can take this quantity at the denominator and express it as a function of z, where z is e to j to pi fs. So you define this polynomial in z, and you express the denominator of spectral music in terms of z. Then we are interested on the roots of this equation. And once we have the roots of this equation in Z, we can find clearly the direction arrival. Why? Why? Because there is this relationship between Z and the spatial frequency. So from the phase of the roots, we get this value here. If we divide by 2 pi, we get the spatial frequency. Once we have the spatial frequency, you multiply by lambda divided by d, and then you calculate the arc sign, and you get an estimate of the direction arrival. So basically, first you find the value of Z, so the k roots of this polynomial, and then from the roots, you find an estimate of the direction arrival. Now, this polynomial, this has order n minus 1. When you multiply by this, it has order 2n minus 1. So there are 2n minus 1 roots. Okay, there is a lemma, there is a result that says that if the polynomial has this structure here, what happens is that half the roots are external to the unit circle and half the roots are internal. So there are n minus 1 external, n minus 1 internal. And the relationship is the following. For any internal root in Z, there is one in reciprocal conjugate position. So if Z is a root, also 1 divided Z Hermitian is a root. So for example, if there is a root for this value of Z, modulo 0.8 and phase pi over 4, there is a root in 1 divided Z conjugate. So 1 divided 0.8, and so the amplitude is the reciprocal, the phase is the same, because you put the reciprocal, but then you take the conjugate. So basically, the roots are aligned couple in couples in reciprocal position with respect to the unit circle. So there are m minus 1 internal, m minus 1 external. We consider those that are closest to the unit circle. Because ideally, for the solution of interest, they should be on the unit circle. But because G is not the exact G, is the estimated one, we assume that the roots, because of the estimation error, moves away from the unit circle, but we consider for our estimate the k roots closest to the unit circle. So there are m minus 1 roots, but we look at the k, this picture 2, closest to the unit circle. So these are the signal roots, and the other are the noise roots. And from the phase of these two, we obtain an estimate of the directional arrival. Now, the situation is this. Maybe the true roots that should be on the unit circle are these two. Then there is an error both in the phase and the amplitude, and so we get these two. Root music rely its estimate only on the phase. So is mostly unaffected by an error in the modulo. Instead, spectral music is affected by an error in the modulo because the farther is the root from the unit circle and the more is the broadening of the pseudospectrum. And so we have a degradation of the performance of spectral music. So spectral music suffer for degradation due to both phase and modulo errors. Root music is affected only by an error in the phase, not in the modulo. So that's why root music has better performance than spectral music. This is the advantage. And also computational complexity is smaller because we don't have to make a search of the position of the peak. So root music is better than spectral music, both in terms of estimation accuracy and in terms of computational complexity. The drawback is that it can be used only for EULA array. Instead, spectral music can be used for any, for example, sparse linear array. Obviously, music, I mean, both of them can suffer for what is called subspace warp errors, because if the noise is so large that one of the noise roots due to the error in the estimation is closer to the unit circle than one of the signal root, basically you have an error because an eigenvector of the noise subspace is considered to be an eigenvector of signal subspace. So there is a swap in the subspace, and the effect on the error is catastrophic, obviously. What's the time? So I think we should have sorry, I wanted to finish this. So we can have half an hour break now.